Hi, in this video we'll discuss credible intervals and how to interpret them. So what are credible intervals? So it's very similar to confidence intervals, except now we're in the Bayesian setting where we have an unknown parameter theta that's a random variable, not a fixed number. Otherwise, it's very similar. Bayesians just like to call things differently. So if we give a single point estimate like we do in MAP, we will never be exactly correct. So again, we want to give an interval and not just a single number. So let's do an example to see how this works. So we want to construct an 80% credible interval for theta, where theta is the unknown probability of success in Bernoulli random variables. And we have 12 samples from the Bernoulli random variable, and we observed 11 successes out of 12. So suppose our prior is beta of 7,3, which basically means that we saw 7 minus 1, or 6 successes, and 3 minus 1, or 2 failures ahead of time. So from the previous video, if we have a beta prior for theta, that leads to also a beta posterior for theta, which is beta 18,4. So this basically means that we've seen 18 minus 1 successes and 4 minus 1 failures. So therefore, our MAP is just 17/20. Okay, so we want an interval now such that the probability that theta lies within the interval is 0.8. So kind of if we draw it on the PDF, we want to find an area here such that the probability that we fall in that area is 80%. So if the area is centered, that makes sense that the probability of being to the left of the interval should be 10% and to the right should also be 10%. But where exactly should we draw these lines? Well, the left boundary should be kind of where the probability of being left of here is 10%. Similarly, the probability of being left of the right edge should be 90%. So this information is given to us by the CDF again. So all we have to do is figure out what value of x has a CDF value of 0.1. Well, that ends up being an x of 0.7089. So the probability of being less than 0.7089 in this beta distribution is 10%. Similarly, for the right side, all we have to do is figure out what value of x has a CDF of 0.9, and that happens to be 0.9142. So that means that the probability of being left of here is 0.9. Okay, formally, if f beta is a CDF of the beta distribution, then we just choose the left bound to be the inverse beta CDF at 0.1, and then b, the right bound, should be the inverse beta CDF at 0.9. So that produces our credible interval. And notice that the MAP estimate is 0.85, which is not at the center of our credible interval. And we could have actually chosen any A or B such that the area between them is 80%. We just chose these so that the areas to the left of the interval and to the right are equal. And of course, the inverse beta CDF seems really weird to compute, but thankfully Python has a function that already just computes it for us. All we have to do is call beta.ppf at 0.1 and then input the parameters of the beta distribution. Okay, so in general, if you have IID samples x1 through xn from some distribution with unknown parameter theta, and we're in the Bayesian setting, so we have a prior distribution over theta, then we can construct a 100 times 1 minus alpha % credible interval for theta, which is an interval such that the probability over the randomness in the random variable theta that theta lies in the interval is at least 1 minus alpha. And if we had chosen the appropriate conjugate prior for the sampling distribution, like a beta prior for Bernoulli, then the posterior is easy to compute. And let's say that the CDF of the posterior is Fy. Then the credible interval can be written by this formula, which is the inverse CDF of the posterior at alpha over 2. So alpha over 2 in our case was 10%. And then the right bound would just be the inverse CDF of 1 minus alpha over 2, which was 90% in our case. Again, this is the interval that contains equal area to the left and right of the interval, but there are infinitely many possible credible intervals you could create. Okay, so how do we interpret these credible intervals again? Well, actually it's now correct to say that there is an 80% probability that theta falls within this credible intervals, or that probability of theta being in this interval is 80%. So this is actually correct to say because now theta is a random variable, so there is a probability that theta falls within that range. Whereas with confidence intervals, theta was a fixed number, so there's no probability in how theta could be. It was fixed. But now in the Bayesian setting, theta is itself a random variable and has a distribution. So that is why this interpretation actually makes sense. Thank you.